In this video, we're going to be creating an AP Physics Unit 5 rotations cram/formula sheet. Let's first start off with rotational kinematics. Rotational kinematics essentially takes the variables that are in linear kinematics, but it swaps the variables. So they're going to be analogous to each other. In linear, we have x, v, and a. And in rotational, we have theta, omega, and alpha. So the core equations that we get from this are going to be omega is equal to theta is equal to omega initial t plus 1/2 alpha t squared So those are the equations you have to know for rotational kinematics. There are a few unit conversions that you have to be able to utilize when you're reporting your final answer. When you have RPM, you want to convert this to radians per second. If you're given an omega, your angular velocity, that is going to be RPM times 2 pi divided by 60. If you have radians per second and want to go to RPM, you have your angular velocity omega is omega rads per second, and you're going to multiply that by 60 over 2 pi. There are a few connections that unite linear and rotational in a few core equations. On to moment of inertia. For a thin ring or hoop, I is mr squared. For a solid disk, I is 1/2 mr squared. For a point mass, I is small mr squared. Now for two masses on a rod, I is equal to the summation of mr squared plus the inertia of the rod. Now for the parallel axis theorem, I is equal to inertia of the center of mass plus mass distance squared. Now, for torque and rotational dynamics, we have torque is equal to RF sine of theta. Torque is equal to moment of inertia times angular acceleration. Torque is equal to tension times R for a pulley. Now, for Newton's second law for rotation and mass, in linear we have summation of forces equals to mass times acceleration, but here we have summation of torque is equal to moment of inertia times angular acceleration. Now for our hanging mass problems, we have a tension force up and we have mg down, and this is our mass, Fg. You have to be careful with signs, as we have, if the mass accelerates downward, this means you have to write this as T minus mg is equal to ma. T minus mg. This is if it's accelerating up. So you can rewrite this as Tm g minus a. Moving on to angular momentum. Angular momentum is defined as moment of inertia times angular velocity. Now, for a particle, we use the form L is equal to mr squared omega, or L is equal to mvr. Conservation of angular momentum. This is when you have no external torque. So that is like when you have conservation of linear momentum, that's when you have no external force. But here torque is going to be the same as our force, as we've seen in F equals to ma. It's going to be torque equals to ia. So then when we have this, similarly just as we have done with momentum, linear momentum, we set these two equal to each other, and you could rewrite this as now you would use this for scenarios where you have a platform and a child, a person pulling arms in, a ring dropped on a disc, a bullet that hits a rod, and also rotational collisions. If you have this platform and a child specifically, if you are initially at rest, L total is equal to 0. So you can write I of the platform, WP platform, plus mr squared omega c is equal to 0. So this is why the platform would rotate opposite. For rotational collisions, you have the form when angular momentum is conserved. Now, if your second object is initially at rest, you would write this instead as I. Or rearrange this for omega f. Now, for a bullet hitting a rod, what you do is you conserve angular momentum about the pivot. So that's your initial. LF is going to be inertia total. And if you solve for omega, that's from setting them equal. Now, let's make a section up here for work and rotational kinetic energy. Your rotational kinetic energy is 1/2 I omega squared. Now your translational kinetic energy is 1/2 mv squared. Your total kinetic energy is going to be both of them. I total omega squared. Now for your energy change in an elastic rotation, you have that your angular momentum is conserved. However, when this is the case, energy is not conserved. So you can write delta K is equal to Kf minus K initial. And this is often going to be negative. Now, you also have to deal with centripetal force. And this is usually going to be when you have friction in play. Fc is equal to mr omega squared. In addition, you have some period relations. Like omega is equal to 2 pi over t. T is equal to 2 pi over omega. Now, in addition, you also have angular momentum of a particle vector, of a particle in vector form. So this is going to be when you have the bullet, you know that angular momentum L is equal to R cross P. Now for the magnitude of this, that's L is equal to R P sine theta. L is equal to mvr sine of theta. So this is like bullet hitting a rod, or when you have any angled impact or any off axis collision, because you take the cross. Now, if velocity is perpendicular, then your angle is going to be 90 degrees. That's going to be 1. Now, we can also discuss, okay, we can also discuss torque as a rate of change of angular momentum. Your external torque is equal to, so that means that if your external torque is equal to 0, then your angular momentum is going to be constant. For example, this is like when we have platform problems, or when you have a figure skater that's pulling their arms in, or a bullet collision about a pivot, or if you have a ring dropped on a disc. Again, something I want to go back to is tangential, let's see here, tangential speed versus angular speed change. So, if you have V is equal to omega R, and if R halves and your angular momentum is conserved, I initial, omega initial, IF, omega F. Since we know that I is going to be proportional to R squared, that means if radius halves, you have this. So that means that omega F is equal to 4 times omega initial. But for your tangential speed, you're going to have that VF is equal to RF omega F. And you're going to have VF is equal to 1/2 R initial for omega initial. This is going to be VF is equal to 2 V initial. So this means that V tangential, it doubles. You also have rotational work. Work is equal to torque times theta, which is the same thing as work is equal to the change in K rotational. Like when you have a child walking in, you also have rotational work, which is work is equal to torque times angle theta. Work is also equal to the change in the kinetic energy that is rotational. For example, when you have a child that is walking in, or when you have rotational acceleration. In addition, you have energy, height, conservation. You can think of this when you have a pulley. So, for example, when you have the flywheel problem, your MGH is going to equal to your loss in your rotational kinetic energy. In addition, there's a second method. You can use, which is 1/2 I omega squared is equal to MGH. In addition, when you have linear plus rotational energy, you have K equals 1/2 mv squared plus 1/2 I omega squared. It combines both. When you have angular momentum in terms of tangential velocity, which I believe we wrote about here, L equals mvr. It can sometimes be easier because V equals R omega, so L is equal to m r squared omega. In addition, sometimes you might have rotational impulse, which is when you have delta L is equal to torque times delta T. At the same time, you may have relative motion problems where you're asked to find a magnitude of something relative to another. So just a refresher on that. If you have a child that walks relative to the ground, W child, omega child, ground is going to equal to omega child platform plus omega platform. Also, if you're taking the energy ratio after an inelastic rotation, you have this set up. But the conditions for this is angular momentum must be conserved, and also your second object was initially at rest. Some other variants that we've seen is when you solve for omega in conservation. Also, when we solve for omega in a child problem with the platform. And in general, remember that if R decreases, that means that omega increases. And if inertia decreases, that means that omega decreases. Remember that angular momentum is conserved if there's no external torque. Kinetic energy is not conserved. Not conserved in inelastic collisions. And internal forces don't change total angular momentum. Only external forces do. Another thing about angular momentum that I want to touch upon is that angular momentum is only conserved about a point only if the net external torque around that point is 0. And when we think about that, it can be kind of tricky when you're thinking about the bullet rod problem. So in the bullet rod problem, what we have is that the pivot force passes through the rod. So because it passes through the rod, that means R is equal to 0. And because of that, that means that your torque is equal to 0. So therefore, your L is conserved.